In this video, we're going to talk about the standard normal distribution, and we're going to focus in on z-scores. So first of all, the normal distribution is also called the bell-shaped curve. And it does state this in its opening paragraph, kind of talking about some of the applications. How most data does tend to follow a bell-shaped curve. Not all, but a lot of data. And when you take a sample, most samples follow a bell-shaped curve. So that's why we're going to study it. It is, I said, it's called the normal distribution. And for the moment, we're going to come back to what they mean by standard, but let's just kind of talk about a little bit of the notation for the normal distribution. So we saw this kind of notation when we looked at the binomial distribution. So when you say x and then you do the little tilde and then n for normal, the two parameters we're interested in are the mean and the standard deviation. In particular, the population mean, population standard deviation. Okay, so we're going to talk about what a z-score is. And then from there, we'll go back and talk about what the standardized normal curve is. So the z-score represents the distance a data value is from the mean in terms of standard deviation. So if you say z equals 1, that means that that data value is one standard deviation away from the mean. In fact, it's actually one standard deviation above the mean. But let me first go ahead and give you the formulas we're going to use to find the z-score. For the population, the z-score is going to be z equals x minus mu over sigma. And x is referring to some sort of data value. For the sample z-score, it's very similar, except instead of using mu and sigma, we're going to use the sample notation, which is x minus x bar over s. So similar, and we'll see that in the next chapter, but that's kind of what we'll use when we're talking about a sample. All right, so here, let's come back to that, the word standard normal distribution. For the standard normal distribution, this is when the mean is 0 and the standard deviation is 1, which basically means every value we're looking at is a z-score. So it's thinking of the normal distribution in terms of z-scores. So the normal distribution kind of sets up like this. I go ahead and draw the bell-shaped curve. We have the mean in the middle, and then we have one standard deviation away. So this represents, oops, let me go ahead and change colors for that. So this will represent a standard deviation away from the mean, and it can go on either side. And whatever those values are, this value ends up being the mean plus the standard deviation, whereas this would be the mean minus the standard deviation. So whatever the mean is, we would set that up in the middle, and then we'd add and subtract the standard deviation away from the mean to form the curve. For the normal, the standard normal distribution, the mean is 1. So, the mean is 0. And therefore that center value is 0. So when I go above and below the mean, the standard deviation I'm using is 1. So this is +1 and -1. So we're talking about being one standard deviation above the mean and one standard deviation below the mean. Okay. This information about the z-scores talks about why we have the negative versus positive. So negative means that we're below the mean. Positive means we're above the mean. And we'll reinforce that idea in just a minute. Let's go ahead and look at this example. So we have a normal distribution with a mean of 5, standard deviation of 6, and they're giving us x equals 17. Let's find the z-score for that. So z is going to equal 17 minus 5 divided by 6, which would give us 12 over 6, which is 2. So this 2 means that this data value, 17, is 2 standard deviations above the mean. Here, I'm going to abbreviate standard deviations above the mean. So visually, we're talking about data that would be over here. It'd be an extra standard deviation. So it's sitting right here above the mean relative to the mean. That's how far away it is. Or you could use this label where you'd be putting the mean as 5 and 6 as a standard deviation. That means that this would be 2 standard deviations above the mean. Okay, so looking at x equals 1, that means then for the z-score, we would be doing 1 minus 5 divided by 6, which is -4/6, which we're going to put in decimal form. Z-scores will be at 2 decimal places, okay? We're going to round it to the second decimal place. So we'll always do that when we're working with the z-score. Oh, sorry, and I forgot the negative. And that matters because what that means is that this is almost 1 standard deviation below the mean, but not quite. It's a little closer than that. So we're talking about being 0.67 standard deviations below the mean. So visually, it's closer to the mean than the first standard deviation. It would be somewhere in here. Or if you're looking at the terms of mean and standard deviation given, not the standard normal curve, it would be there. So just so we're clear, these are all z-scores. All of these values over here are z-scores. Whereas all these values, these are the x values. These are the data values. The values given to us from the data. Okay, so summarizing this then, when z is positive, x is above or to the right of the mean, and when z is negative, x is to the left or below the mean. Okay, let's go ahead and look at another example here. Some doctors believe a person can lose 5 pounds on average in a month by reducing his or her fat intake by exercising consistently. Suppose it has a normal distribution, and we will use a standard deviation of 2 pounds. And let's go ahead and fill in the information that they're asking us for. So suppose a person lost 10 pounds in a month. Z-score when x equals 10 is 2.5. So let's just verify that. To verify that, that means that we're doing z equals 10 minus 5, because 5 is the mean, divided by 2, which is going to be 5/2, which 5 divided by 2 is 2.5. So yes, it is 2.5. We verified it. This z-score tells you that 10 is 2.5 standard deviations to the, and now because it's positive, it would be to the right of the mean, which is 5. Okay, so then suppose a person gained 3 pounds. So we're thinking of that as a negative weight loss then. That means that as a z-score, we want to find what that's going to be for this example. So let's go ahead and calculate that. I'm going to do it in the same little space here. So z is going to be -3. So that's a negative weight loss. And then minus 5 divided by 2. So that's going to come out to -8/2, which is -4. So that's our z-score. So this tells us that x equals -3 is 3 standard deviations to the left. Oh, I'm sorry, 4. Just kidding. 4 standard deviations to the left of the mean. This is based on the z-score. All right, so here's kind of the big final example, and it kind of gives us a really great application of what z-scores allow us to do. So suppose you take two exams and you scored an 84 on your statistics exam. And then you were told the mean for the class. So overall, you were above the mean. The mean was 78 and a standard deviation of 10. You scored 87 on your chemistry exam with a mean of 80 and a standard deviation of 12. So both exams you did better than the average. The question is, which one did you actually do better on? So we're comparing it to the rest of the class and how much better you maybe have done on the exam. So if we look at their Z-scores, we'll see how far above the mean they are in terms of standard deviation. So let's start with the stats exam. I'm going to do the Z-score. I'm going to do Z sub S to represent the stats exam. So it was a score of 84 minus the mean of 78 divided by 10. So let's see, that's going to give me 4, 5, 6, so 6 over 10, which is 0.6. So almost one standard deviation, but not quite. Okay, for the chemistry then, we would do 87 minus 80 divided by 12, which would give us 7/12. And when you divide 7 by 12, that gives you 0.58. Oops, put the 0 in front like I did with the last one. So you did do better on stats. Barely, but you did. They were very close in terms of how you performed. But overall, you did better on the statistics. So the Z-score gives us a way of comparing data that really doesn't relate to each other, but we can kind of force it to relate to each other by looking at how far the data value is from the mean in terms of how that data is measured. And that's where it's going to be very useful for us.